It's November 4th, 2025. 3i Atlas has just passed its perihelion, rushing closer to the Sun than any interstellar object ever confirmed. For months, astronomers around the world prepared for this exact week, expecting a bright, predictable outburst as the heat tore through its surface. But that isn't what happened. Instead of flaring, 3i Atlas dimmed. Instead of releasing gas or dust, it stayed intact, silent, and strangely stable as it crossed the most dangerous part of its orbit. The Solar and Heliospheric Observatory recorded a distinct drop in brightness just hours after closest approach, a sharp decline that contradicts every model used to predict its behaviour. The dust plume everyone anticipated never formed. In ultraviolet imaging, 3i Atlas held its shape, dark against the light of the corona, as though it were absorbing energy rather than scattering it. Atacama's infrared stations registered a temperature decrease, not an increase, as if the object was radiating less heat the closer it got to the Sun. Across Europe and Japan, radio telescopes registered a final reflected pulse, and then complete silence. During that window, for nearly 6 hours, 3i Atlas disappeared from every tracking array before reappearing slightly off its projected trajectory. Some scientists have suggested data interference, temporary saturation, or solar background noise. Yet independent teams using different instruments and wavelengths reported the same pattern within minutes of each other. The alignment of those readings leaves little room for coincidence. What happened near the Sun remains unclear, but it's now certain that the perihelion of 3i Atlas wasn't just a passage. It was an event. Something changed out there, something that normal physics hasn't accounted for. Within hours of perihelion, the light curve of 3i Atlas began to fall. Photometric readings from SOHO's LASCO instrument, the STER-EOA coronagraph, and several ground-based observatories all registered a steady decrease in brightness that defied every thermal and reflectivity model previously calculated. Normally, a comet-like object brightens dramatically as solar radiation heats volatile compounds on its surface, creating jets that scatter sunlight. Yet 3i Atlas showed the reverse, a controlled dimming that looked almost deliberate. At first, analysts believed it was a sensor issue. Solar proximity often blinds instruments, especially when the object passes within a few degrees of the corona. But the timing didn't match that explanation. The drop began only after the object had cleared the Sun's limb and should have been easier to observe. Its light returned not gradually but abruptly, as if a switch had been thrown. In the photometric logs from November 2nd and 3rd, the data form a near vertical slope downward, a pattern rarely seen outside of eclipsing binaries or artificial occultations. The intensity decreased by nearly half within 4 observation cycles, then stabilized at a lower level that has remained constant since. No dust trail, no debris fan, no luminous gas cloud appeared to explain the loss of reflected sunlight. Teams at the European Southern Observatory cross-checked the results, using different filters and atmospheric correction algorithms. The numbers held. At 12:47 UTC on November 2nd, the measured magnitude fell sharply, holding near baseline for the next 24 hours before partial recovery. It wasn't random noise. The curve was clean, symmetrical, and abrupt. When analysts mapped that curve against the object's trajectory, they noticed another pattern. The drop coincided with the moment 3i Atlas reached the midpoint of its closest solar approach, the very instant when its exposure should have been greatest. Instead of flaring, it dimmed. The odds of a natural body doing that under such conditions are astronomically low. Spectrographs taken during the same interval revealed something even stranger. The visible wavelength readings flattened, meaning the object was reflecting light evenly across multiple bands, as if its surface properties had changed. Normally, solar heating darkens carbonaceous materials or causes bright silicate plumes, but the readings showed neither. 3i Atlas became a neutral grey source, absorbing more than it emitted. Some theorists now propose that the drop may represent a phase transition, a shift in material structure that allowed it to store incoming radiation. Others argue it's an observational illusion caused by alignment with the solar magnetic field. Yet neither theory explains the synchronized pattern detected from independent instruments in Chile, Hawaii, and Japan. For astronomers tracking the event in real time, the moment felt like watching a signal fade from a distant transmitter. The brightness didn't decay randomly. It fell smoothly, predictably, like an engineered curve. That precision is what unsettled researchers most. When the data was plotted over time, it produced a curve resembling a controlled dimming pattern rather than a chaotic one. Natural phenomena rarely behave that way. To lose brightness in such a narrow window without physical disintegration suggests either shielding or active modulation. And that leads to a new question few are willing to ask publicly. Did 3I Atlas hide itself? The thought may sound speculative, but the timing and geometry make it hard to dismiss. If the object possesses a reflective layer or internal mechanism capable of redirecting sunlight, the apparent dimming could represent a deliberate act, one designed to reduce visibility at the moment of maximum observation. For now, no official statement has been made. Observatory teams continue analysing the light curve across multiple wavelengths, hoping to isolate a thermal or structural cause. But as each dataset is verified, the anomaly only strengthens. The dimming was real, precise, and global. In every known case of a comet or interstellar body approaching the Sun, the process is violently predictable. The surface heats, volatile sublimate, and gas jets burst outward, forming a coma of vaporized material that glows as it catches sunlight. The closer the object moves to perihelion, the brighter and more diffuse it becomes. That's what everyone expected from 3I Atlas. Yet this time, something completely different unfolded. When the Solar and Heliospheric Observatory released its latest coronagraph images, scientists immediately noticed what wasn't there. There was no tail, no haze, and no trace of dust scattering. The region surrounding 3I Atlas remained unnervingly clean, a sharp contrast to the brilliant, turbulent wake that accompanies most near-solar visitors. It moved like a sealed fragment of polished metal gliding through plasma, bright enough to be detected but never spilling material into space. That absence of dust is not just unusual, it's nearly impossible for a natural object of this composition and proximity. At a perihelion distance of just under 0.23 astronomical units, the solar flux should have heated its surface above 800 Kelvin, easily enough to vaporize frozen carbon dioxide, silicates, and even some metals. Under those conditions, dust should have erupted in streams. Instead, nothing. The detectors recorded a uniform luminosity profile that matched neither a gas jet nor a debris field. Infrared readings confirmed the anomaly. A cometary coma emits strongly in thermal bands, but the Atacama array showed none. The background radiation around 3I Atlas remained constant, suggesting no outgassing or particulate generation. When the James Clerk Maxwell Telescope compared this to archived readings from Borisov and Oumuamua, the difference was stark. Those interstellar objects exhibited chaotic, uneven emission lines. 3I Atlas, by contrast, stayed stable, quiet, and tightly bounded. Astronomers proposed several natural explanations. The first was composition. Perhaps the object is composed entirely of refractory materials, metals or dense silicates that resist sublimation. But that theory falls apart under pressure analysis. Even iron-nickel composites would radiate a detectable tail of ionized gas at that range. The second idea involved orientation. Maybe 3I Atlas rotated in such a way that its illuminated surface faced away from Earth, concealing its outgassing. Yet multiple observatories from different longitudes and latitudes reported the same clean halo, meaning the geometry can't explain the total absence. A more unsettling hypothesis soon emerged. Some researchers began to question whether the surface of 3I Atlas might be coated or shielded in a way that actively prevented material loss. Certain alloys, especially those with high albedo and low emissivity, can reflect and absorb radiation in controlled ways. The light curve analysis supports that idea. A sharp drop in brightness during perihelion followed by stabilization could indicate that the surface dynamically adjusted its reflectivity, almost as if it responded to exposure. This possibility gained attention when a team from Kyoto's Department of Planetary Science released a cross-polarization study of the incoming light. They found that the polarization angle of reflected photons shifted in a consistent rhythmic pattern over time, behavior usually associated with structured surfaces. Natural regolith tends to scatter light randomly. A rotating engineered surface, however, can create interference patterns that oscillate predictably. 3I Atlas displayed exactly that signature between November 2nd and 3rd. If this finding holds, it means the object's exterior might not be a solid rock at all but a shell, a layered boundary designed to withstand solar radiation. The shell hypothesis fits other data as well. During perihelion, the observed luminosity briefly stabilized before dropping, suggesting that internal heat did not escape freely into space. That implies insulation or energy retention, something that no comet nucleus or asteroid exhibits naturally. Meanwhile, the absence of dust continues to trouble analysts working at NASA's Goddard Space Flight Center. They've run thermal simulations under dozens of conditions, varying composition, density and spin rate, yet none reproduce the observed stability. Every natural model ends with the same outcome: partial fragmentation or a significant brightening event. But 3i Atlas glided through its perihelion unchanged, as though solar energy were nothing more than a passing inconvenience. Data from the STER-EOA spacecraft added another detail. Its wide-field camera detected faint diffraction fringes trailing behind the object, not dust, but electromagnetic interference patterns, like light bending through a thin invisible sheath. The spacing of those fringes remained consistent for 3 consecutive frames, suggesting a coherent field rather than random scattering. If real, it points to a phenomenon that interacts with sunlight in an organized manner, possibly magnetic or electrostatic. Several independent researchers have begun to refer to this pattern informally as the solar mirror effect. It suggests that 3i Atlas either generates or carries a surrounding field that repels solar particles. In such a case, dust never escapes because charged material is immediately redirected back to the surface or absorbed. No known natural mechanism could sustain that balance under such proximity without collapse. Of course, the idea of an object actively protecting itself near the Sun sounds speculative, but so far data supports no simpler alternative. When Comet C/2025-02 Swan passed perihelion earlier this year, its dust production increased tenfold. The contrast with 3i Atlas could not be sharper. One object behaved like a fragile natural body, the other like something managing its own thermal load. What makes the brightness pattern even more perplexing is its smoothness. Across 3 days of continuous monitoring, no fluctuations appeared. Most natural objects flicker slightly due to spin, albedo variation, or outgassing events. 3i Atlas remained flat-lined stable, almost as though its surface were uniformly reflective and rotating in perfect synchronization with its orbit. For astronomers accustomed to randomness, that kind of precision feels unnatural. When the European Space Agency plotted its reflectivity profile against time, the result resembled a modulation curve, the kind used in radio engineering to describe controlled brightness variation. No one is claiming it's artificial, but the mathematical resemblance is uncanny. The amplitude, frequency and phase match a pattern of deliberate dampening, not chaotic natural drift. Critics argue that this may be coincidence or that the perceived regularity comes from instrument calibration overlap, but those counter-arguments fade under the weight of redundancy. The same dustless brightness pattern appears across 6 independent systems, each using unique instruments, sensors, and atmospheric corrections. The chance that all of them misread the same behavior in the same direction is effectively zero. A quiet unease now hangs over the International Observatory Network. Every researcher understands what the absence of dust means. Either 3i Atlas is made of material unknown to current science, or it's encased in something not naturally occurring. The more data they collect, the clearer that choice becomes. At this stage, scientists are no longer asking whether 3i Atlas is unique. They're asking how long it has been behaving like this, and whether the anomaly extends beyond optical wavelengths. That question is now turning attention to the deeper, invisible parts of the spectrums, radio and infrared, because while the visible range reveals silence, those deeper frequencies might expose movement, pulse, or change within. And that's where the next mystery appears. Just as its light faded and dust refused to emerge, something else vanished. The radio echoes. The object that should have scattered radar beams back toward Earth went completely dark to the antennas designed to trace it. By the morning of November 3rd, the first complete spectrographic datasets from 3i Atlas's perihelion began circulating among observatories. When researchers overlaid the pre-perihelion and post-perihelion spectra, the change was immediate and undeniable. The object's colour signature, once dominated by a pale blue reflection typical of metallic silicates, had shifted toward a flattened neutral tone. In practical terms, that means its surface stopped behaving like a reflective mineral and began acting more like a light absorber. This change occurred within hours. right as the object exited its closest solar approach. Normally, exposure to such intense radiation burns off volatile layers and reveals a darker, carbon-rich core. But the colour transition seen here wasn't darkening, it was spectral compression, the wavelengths of reflected light converging toward a uniform grey without any sign of carbon absorption lines or silicate resonance peaks. That flattening implies a surface that's suddenly restructured at a molecular or crystalline level. It's the kind of shift you might expect if the object's outer shell had melted and reformed into something smoother, denser, and more optically consistent. Spectroscopy from the Subaru telescope in Hawaii revealed that the characteristic 1.05 micron absorption band, common in oxidized minerals, vanished completely. At the same time, faint emission spikes appeared around 850 nanometers, a wavelength not typically seen in reflective solar system objects. Some researchers initially dismissed this as interference from solar background noise, but after cross-checking with the Very Large Telescope in Chile, the spike persisted. Two independent instruments, thousands of kilometers apart, observing the same anomaly within minutes of each other. That emission spike is what turned a routine spectral analysis into a point of contention across the global astronomy community. Its amplitude was small, less than 1% of total reflected light, but it pulsed at consistent intervals, roughly every 9 minutes. Such rhythmic fluctuations are rarely seen in reflected spectra, and when they do appear, they're usually linked to rotational modulation. Yet 3I Atlas's spin period doesn't match that timing. The pulse occurred independently of rotation, as if originating from within the object rather than from its reflective motion. Infrared telescopes picked up something similar. The Atacama Pathfinder experiment recorded a narrowband anomaly at 4.3 microns, where carbon dioxide normally emits during sublimation, but instead of the expected wide plume signature, there was a discrete high-coherent signal lasting for nearly half an hour before cutting off sharply. That behaviour doesn't resemble gas release, it resembles resonance, a harmonic emission produced when energy cycles through a confined medium. If the object were hollow, partially metallic, or structured internally, it could theoretically resonate like that under solar stress. The energy would enter, reflect off internal surfaces, and re-emit in short bursts. That's one possible explanation. Another, more controversial, is that the emission could represent active discharge, stored energy being released in a timed sequence. Whatever the cause, this spectral behaviour has no precedent in interstellar observation. Even Oumuamua, with its mysterious acceleration, never exhibited a measurable emission spectrum. Its surface reflected light passively. 3I Atlas, however, seems to interact with sunlight dynamically. The Kyoto analysis team ran a comparative simulation of how a layered, nanostructured surface might behave under solar flux. They modelled it as alternating layers of conductive and insulative material, similar to metamaterials designed on Earth to manipulate electromagnetic waves. The result matched the observed pattern almost perfectly, a flattening of reflectivity across the visible spectrum and discrete emission spikes in the near-infrared. That doesn't prove 3I Atlas is artificial, but it suggests its surface behaves like something built for energy control, not geological chance. Even the most cautious scientists admit this is difficult to rationalize naturally. To alter its entire spectral signature within a few hours would require a process faster than any known phase transition in silicate or metal compounds. The only comparable transformation would be vaporization and recondensation, yet no mass loss was detected. The brightness drop seen earlier did not coincide with increased solar reflectivity, as would be expected if the object had erupted gas. It simply changed colour. Astronomers describe this as optical metamorphosis, an abrupt shift in the way light interacts with the object's surface. The question is why? Some propose that solar radiation pressure compacted or reorganized dust layers on the exterior, smoothing the surface until it reflected uniformly. But that idea collapses when confronted with the absence of dust itself. There was nothing to compact. The dustless brightness seen earlier proves the outer layer wasn't particulate. Others point to magnetic induction. As 3I Atlas passed through the Sun's magnetic field, electric currents could have been induced within its structure, altering its surface properties. Yet that mechanism would generate visible plasma arcs or heat emission, neither of which were observed. The object's thermal profile stayed cool, unnaturally so. In parallel, data from the Deep Space Network showed a subtle frequency-dependent delay in radar reflections from before perihelion compared to after. The post-event echoes returned fractionally later, as though the radar waves had travelled through a medium slightly denser than before. It's a minor delay, milliseconds at most, but consistent across multiple frequencies. This could mean that 3I Atlas's surface density changed, or that a thin atmosphere of charged particles temporarily surrounded it after perihelion. Either possibility reinforces the notion that the object underwent an active transformation. At Harvard's Astrophysical Data Center, a group of analysts overlaid the new spectra on historical records from 3I Atlas's initial discovery phase. The difference was striking. The early data displayed small fluctuations and natural noise, the kind expected from rotation and texture variation. The post-perihelion data is smooth, mathematically precise, and repeats with clock-like accuracy. Natural processes produce randomness. This, on the other hand, looks like calibration. It's that sense of precision that's driving debate within research circles. An object behaving this consistently across such extreme conditions challenges the definition of natural behaviour. A rock cannot decide to become optically neutral. A frozen nucleus cannot emit narrowband resonance without thermal chaos. Something inside 3I Atlas is managing its interaction with sunlight, whether by physical structure or by unknown physics. The global astronomy community is now divided. Some hold that the spectral shift marks the discovery of a new class of interstellar material, one capable of surviving solar radiation through self-regulating reflectivity. Others, more quietly, consider the possibility that the shift represents a signal of function rather than of substance. If 3I Atlas is an engineered relic, then perihelion might not have damaged it at all. It might have activated it. But the most immediate consequence of this discovery is practical, not philosophical. The spectral flattening has made 3I Atlas far harder to track. Its neutral reflectivity reduces contrast against the solar background, making optical detection difficult even with advanced telescopes. What was once a bright blue-tinted anomaly has become a grey phantom. That's why, since November 3rd, the tracking arrays in Arizona and Chile have struggled to maintain a lock. The object simply blends into space. As this silent transformation continues, a secondary mystery deepens. One not about light, but about sound, or the lack of it. The Deep Space Network's listening arrays, which had been bouncing radar pulses off 3I Atlas since September, suddenly reported total radio silence during perihelion. No reflected signals, no returns, nothing but a blank field where the object should have been. By the afternoon of November 3rd, the first orbital recalculations for 3I Atlas began circulating among the deep space tracking teams. When the data from NASA's JPL Horizon system was compared with readings from ESA's Near-Earth Object Coordination Center, one inconsistency stood out. The object's projected path no longer matched its real one. The offset was small, a few arcseconds in angular terms, but significant enough to suggest that 3I Atlas had experienced a force not accounted for by gravity, solar wind, or outgassing. Something nudged it. This offset first appeared in the combined datasets of the Solar and Heliospheric Observatory and the TEREOA spacecraft. Both had monitored 3I Atlas before and after perihelion. In the hours following its closest solar approach, the object re-emerged from behind the Sun slightly ahead of schedule, roughly 27 minutes earlier than predicted by gravitational modelling. To the untrained eye, that's minor, but astronomically it implies an unmodeled acceleration. The heliocentric velocity should have decreased due to solar drag and radiation pressure, yet it increased. NASA's Jet Propulsion Laboratory ran several simulations to explain the shift. The first model tested the possibility of asymmetric outgassing, a natural process where jets of vaporized ice act like small thrusters. That mechanism has been observed before, most famously in Comet 67P and Oumuamua. But the results didn't align. For such a trajectory change to occur, the mass loss would have needed to exceed 10 to the 6th kilograms, generating visible dust trails and infrared emissions. None were detected. The next hypothesis involved solar wind. During perihelion, the Sun's charged particles can impart measurable momentum to objects with large surface areas. But 3I Atlas's surface-to-mass ratio is too low for radiation pressure alone to explain the observed deviation. The acceleration vector also points in the wrong direction, not away from the Sun, but slightly transverse to its orbital path, as though the object adjusted its course sideways rather than being pushed radially outward. Analysts then tested a third variable, gravitational perturbation by unknown nearby bodies. Nothing significant was found. The region around perihelion was empty, and no small companion objects were recorded by SOHO's coronagraphs. The offset therefore cannot be attributed to gravitational interference. That left a troubling conclusion that 3i Atlas altered its trajectory by means not accounted for in natural modelling. The deviation was clean, linear and controlled, not random or chaotic. Its new path suggests a calculated impulse rather than a thermal or mechanical reaction. To put this into perspective, comets and asteroids don't change direction smoothly. When they fragment or vent gas, their paths jitter, wobble and decelerate. What happened here was the opposite. A stable increase in velocity and a near-perfect adjustment of orbital inclination by roughly 0.03 degrees. That's not much, but it was executed in a way that maintained orbital coherence, as if the object compensated for solar drag in real time. Observatories in Japan, Chile and South Africa confirmed the same offset using independent instruments. The error margins matched to within a few hundredths of a degree. This eliminated the possibility of calibration faults or timing discrepancies between systems. When every station, using different optical setups, reports the same offset, coincidence stops being plausible. The analysts working on the Deep Space Network tracking logs noticed another subtle signature. The Doppler frequency of the radar echoes, right before they vanished, contained a gradual upward drift inconsistent with passive motion. That drift represents a change in velocity of a few millimeters per second per minute, precisely the kind of continuous acceleration that would produce the observed path deviation. Some have described it as a microburn, a term borrowed from spacecraft operations. The idea is that 3i Atlas may have undergone a sustained impulse rather than a single event. If so, the acceleration occurred exactly when the object was least visible, during the 6-hour radio blackout. The timing aligns perfectly. This raises an uncomfortable question. If 3i Atlas can alter its trajectory, how? No known natural mechanism can generate thrust without mass loss or external interaction. One possibility under discussion involves electromagnetic propulsion. If the object has a conductive shell or internal magnetic field, it could theoretically interact with the sun's plasma to produce motion, using Lorentz forces much like a magneto-hydrodynamic drive. The solar magnetic field near perihelion is strong enough to provide coupling energy for such an effect, but only if the object can control its orientation precisely. The stability observed in 3i Atlas's spin makes that theoretically feasible. ESA's Planetary Defense Office has quietly begun reclassifying the object's trajectory status from passive to active, a designation used for bodies that show self-induced movement. Internally, that term doesn't imply intelligence, only that an unexplained impulse has been observed. But the implications are the same. 3i Atlas is no longer considered dynamically inert. The offset itself may appear minor, yet its pattern holds meaning. When plotted over time, the deviation follows a smooth sinusoidal curve, with gradual acceleration and deceleration phases rather than abrupt changes. That's the hallmark of controlled thrust modulation. Natural phenomena produce jagged, unpredictable lines. This one is clean and continuous. Observers from the Subaru telescope noted an additional clue. The object's rotational vector shifted subtly after perihelion. Prior to its close approach, 3i Atlas rotated once every 7.14 hours. Post-perihelion, that period increased by just under 2 minutes. The deceleration is too small to attribute to tidal forces or impact, suggesting internal redistribution of angular momentum. It's as though the object adjusted its spin to stabilize after a maneuver. Such changes demand immense energy precision. Even slight errors in force application would have sent 3i Atlas tumbling chaotically, yet it remained perfectly balanced. The orbit it now follows differs only slightly from the one projected months ago, but the control implied by that subtlety is what makes it extraordinary. A few researchers have tried to frame the event within the context of interstellar dynamics. They argue that 3i Atlas could be composed of ultra-dense material that reacts to radiation pressure in nonlinear ways, causing microthrust from photon momentum. However, this model fails to explain the specific timing. If radiation pressure were the cause, the deviation would have developed gradually before perihelion, not abruptly afterward. The The global tracking network has since recalibrated its predictive models. Every new dataset confirms that 3i Atlas's heliocentric velocity now exceeds the pre-perihelion estimate by roughly 24 meters per second. That's too precise to be coincidence, too small to be explosion, and too consistent to be random. One internal memo from ESA's Trajectory Analysis Division described the finding with clinical restraint. Observed post-perihelion vector shift suggests an impulse event coinciding with untracked interval. Directionality implies internal control mechanism or interaction with solar plasma. Pending verification, no agency has publicly confirmed that statement yet, but within the research community, it has become the quiet consensus. Whatever happened near the Sun was not passive. The motion of 3i Atlas implies coordination, whether mechanical, electromagnetic, or something still outside current models. For astronomers who have spent years insisting on natural explanations, this is a turning point. They can no longer treat 3i Atlas as a drifting relic. It behaves as though it can respond to its environment, alter its path, and regulate its exposure to the Sun. In the days following the offset detection, something else began to trouble analysts. While optical tracking confirmed the object's new position, the radio echoes never returned. The light showed movement, but the sound, the radar, stayed silent. It's as if the same mechanism that changed its trajectory also absorbed or redirected the radar pulses. That link between physical movement and electromagnetic silence forms the next phase of this investigation. Because if 3i Atlas truly initiated a maneuver, the blackout that followed might not be coincidence. It might be part of the same event. From the moment 3i Atlas crossed behind the Sun, radio telescopes worldwide prepared for brief interference. Solar conjunction always produces a few hours of degraded signal caused by plasma scattering between Earth and the target. But when the object emerged again, the expected radar echoes never came back. Deep Space Network antennas in Madrid, Goldstone and Canberra all reported the same result. Silence. No reflections, no Doppler feedback, no trace of radar bounce. Even at low-gain frequencies, where debris or diffuse gas clouds usually return faint echoes, there was nothing. It was as if the object had absorbed every signal sent its way. The first to notice the anomaly was a tracking team at the Goldstone complex in California. Their systems were running a routine cycle at S-band and X-band frequencies, alternating between 2.3 and 8.4 GHz. Normally, radar pulses sent toward a near-solar object scatter enough energy to produce at least a background curve of noise. This time, the readings were flat. Technicians initially assumed the transmitters had malfunctioned under solar interference, but calibration checks confirmed everything was operational. When Canberra reported identical readings hours later, and then Madrid, the pattern became undeniable. 3i Atlas was radio dark. What made this more than a technical glitch was timing. The blackout began precisely during the 6-hour interval when optical systems lost visual contact near perihelion. By the time it should have reappeared, radar had gone silent as well. It was the first total communication gap across all wavelengths since the object's discovery. In past conjunctions with other near-Sun bodies, radar had always returned some fragmentary data, even when visual imaging was impossible. This time, the universe returned nothing but static. A NASA engineer described the phenomenon in an internal summary. Radar transmission normal, no reflection within error window, target position uncertain. Signal absorption appears total. That phrase, signal absorption, quickly became the center of debate. Absorption implies interaction, a mechanism capable of capturing or neutralizing radio energy. A comet can scatter or weaken a radar beam, but it cannot erase it. The ESA's Cebreros station ran emergency sweeps across alternate frequencies. They lowered the transmission power, switched polarization angles, even inverted signal phase to look for phase-shifted reflections. Every attempt produced the same result: complete loss. The radar pulses vanished into the void. On the spectrograms, the bands that usually glow with faint echoes looked like an empty corridor. Some suggested that the silence was a byproduct of the trajectory offset. If 3i Atlas's path had shifted slightly, radar beams might have been pointed off target. But orbital recalculations dismissed that theory quickly. The offset was far too small to remove it from radar coverage, and even a miss would have produced side lobe reflections detectable at nearby angles. There were none. Attention then turned to the solar environment itself. Could plasma density have absorbed the signals? Space weather logs from the Solar Dynamics Observatory showed mild activity. Small coronal mass ejections, none strong enough to cause global radar blackout. The background noise levels remained stable. This wasn't a solar interference event. The silence wasn't coming from the sun, it was coming from 3i Atlas. When spectrographs were overlaid on radar transmission times, something even stranger emerged. The faint emission spike around 850 nanometers, the one first noted during the spectral shift, pulsed in near-perfect synchronization with the radar transmission windows. Each time ground stations fired radar bursts, that optical spike brightened by a fraction of a percent, then faded. It was as if the object registered the incoming signals, reacted, and emitted faint bursts of light in response. Light that carried no return signal, only confirmation of interaction. The pattern repeated 6 times before the optical spike vanished entirely. Analysts in Japan, monitoring through the Nobiyama Radio Observatory, cross-checked the timing. Their data confirmed the correlation. The implication was chilling. 3i Atlas wasn't just silent, it was responding. One possible natural explanation is radar heating. When an object absorbs radio energy, its surface can re-radiate part of it as infrared or visible light. That might explain the synchronized flashes. Yet the energy levels don't match. The radar power transmitted towards 3i Atlas was insufficient to generate such optical response at that distance. The conversion efficiency would have to exceed 100%, an impossibility under known physics. If the correlation is real, then 3i Atlas either amplifies incoming radio energy or channels it internally before releasing it as light. That behavior resembles active signal management, not reflection, but modulation. A few engineers even joked uneasily that the object listened before going dark. After the final radar attempt failed, observatories began using passive listening instead of active transmission. They tuned receivers to wideband frequencies, hoping to pick up any residual emissions. For 2 nights straight, nothing appeared. Then, early on November 4th, the Charnantor array in Chile detected a narrow, ultra-low frequency hum near 3.1 Hz. Too low to be ordinary radio, too coherent to be background noise. The signal lasted 40 seconds, repeated once, then stopped. That hum was never heard again. Whether it originated from 3i Atlas or from solar interaction remains uncertain, but its timing, within minutes of radar silence confirmation, deepened the mystery. At this stage, what began as a data gap turned into a full spectrum phenomenon. No radar, no standard radio, no reflected signals of any kind. Even the polarized solar wind particles showed altered deflection patterns around the region where 3i Atlas should have been. Magnetometer readings indicated a localized drop in plasma density, as if something there was absorbing or deflecting charged particles, not simply passing through them. Theories multiply with every dataset. Some researchers point to plasma cloaking, a theoretical process where an electromagnetic field could suppress radar reflections by ionizing the surrounding medium. In principle, a sufficiently strong, organized magnetic field could create a radio shadow, rendering an object invisible to radar while still interacting with sunlight. But the energy required for such a field is immense. No natural object of that size could sustain it. Others argue that the silence is more psychological than physical, that analysts are reading coherence into noise. But the redundancy of independent observatories contradicts that. 3 continents, multiple instruments, all reporting the same zero return. When enough data sources agree on absence, absence itself becomes evidence. The more pragmatic interpretation is that 3i Atlas entered a state of electromagnetic transparency. Certain crystalline or metallic structures, when exposed to intense solar radiation, can change their dielectric properties, allowing radio waves to pass through without reflection. That would explain the loss of radar echo. The energy isn't absorbed or scattered, it simply passes through. Yet if that were true, detectors behind the object should have seen the signals continue on. They didn't. The waves didn't pass through, they disappeared. During internal reviews, one ESA scientist summarized it bluntly. It's as if 3i Atlas switched to stealth mode. The phrasing was informal, but the implication serious. The object behaved like something capable of altering its electromagnetic profile deliberately. dimming its brightness, neutralizing its reflection, and modifying its orbit all within 48 hours. The silence continues to this day. Every attempt to ping the object since November 3rd has failed. Even low-frequency radar used for tracking near-Earth asteroids yields no return. The region where 3i Atlas should be is geometrically confirmed, but electrically blank. It's there, yet it's not interacting with any known form of transmission, and while radar silence might seem like the end of the trail, it's actually where a new mystery begins. Because as the signal stopped, a strange glow began to form around the position where the object should have been, a faint expanding ring seen not in light, but in polarization. Whatever blocked the radio waves didn't stop the surrounding plasma from reacting. That reaction, observed by coronagraphs and magnetometers, revealed something invisible becoming briefly visible. Not a tail, but a symmetrical halo forming around emptiness. In the early hours of November 4th, as ground-based radar arrays reported continued silence, the Solar and Heliospheric Observatory transmitted an image that immediately reignited debate across the scientific community. The coronagraph frames showed a faint circular glow surrounding the coordinates where 3i Atlas should have been. A perfectly symmetric halo expanding outward against the backdrop of the Sun's corona. It wasn't a dust plume, it wasn't solar flare interference, it was a geometric ring, uniform in intensity, centered precisely on the last recorded position of the object. At first glance, the phenomenon looked like a lens artifact, the kind of false halo that occasionally appears when light from the corona reflects internally within the detector. But instrument specialists at SOHO dismissed that theory within hours. The halo appeared on multiple cameras with different optical systems, LASCO C2, LASCO C3, and Stereo A's wide-angle imager, each using distinct angles and calibration parameters. 3 instruments, 3 perspectives, 1 identical ring. The structure was unmistakable. It had a radius of roughly 40,000 kilometers and expanded at a constant rate of about 8 kilometers per second before fading into invisibility over the next 5 hours. The brightness profile was unusually smooth, lacking the turbulence or granular scattering associated with gas or dust. It resembled an electromagnetic field visualization more than a physical cloud. No material emission was detected in visible infrared or ultraviolet bands. The only confirmation of its existence came from polarization measurements, which showed a sudden and localized rotation of light vectors as they passed through the region. That polarization rotation implies interaction with a magnetic or electric field, something transparent, charged, and coherent enough to distort the orientation of photons. In simple terms, light bent around nothing. It was a field without mass. ESA analysts working from the European Space Operations Centre called it the halo anomaly, and the name stuck. What puzzled them most wasn't the symmetry itself, but the timing. The halo began forming less than an hour after the final radar echoes disappeared, as though the two phenomena were directly linked. If 3i Atlas had indeed become electromagnetically transparent, this ring might represent the boundary of that transformation, the signature of whatever process rendered it undetectable. The Atacama Large Millimeter Array recorded subtle disturbances in local radio polarization during the same window. Those disturbances matched the spatial radius of the halo seen by SOHO. Atacama's instruments, designed for deep sky cosmic background studies, are sensitive enough to detect variations in magnetic fields measured in nanoteslas. They picked up a brief pulse, expanding outward and fading, the same temporal pattern as the halo's light rotation. NASA's Goddard Solar Physics Laboratory tried to model the event. Their simulation treated 3i Atlas as a charged conductive body moving through the Sun's magnetic field. Under certain conditions, an intense induction could produce a transient plasma envelope, a symmetric shell of ionized particles that refracts light without emitting it. This might explain the observed ring, but not its uniformity. Plasma events near the Sun are chaotic. This halo was geometrically perfect, stable, and evenly distributed, which implies regulation. By midday, data from STE-REOA confirmed a second layer expanding behind the first, fainter, slower, and almost invisible without enhanced imaging. 2 concentric rings moving outward from a single point in space. The inner halo dissipated quickly, but the outer one lingered, detectable through polarization, mapping for nearly 9 hours. Its persistence suggests that whatever produced it had a lasting electromagnetic influence, strong enough to realign local plasma flows. Several observers compared the event to the Earth's auroral ovals, luminous rings caused by charged particles funneled by magnetic fields. But the analogy breaks down under scale. The energy required to generate such a structure near the Sun exceeds any natural process known to operate on an object the size of 3I Atlas. The Sun's corona itself is full of high-energy plasma, yet even there, magnetic arcs twist irregularly. This halo was disciplined, concentric, and mathematical. The phenomenon wasn't purely visual either. The Parker Solar Probe, which happened to be monitoring solar wind density during that period, recorded a brief dip in particle flux precisely aligned with the halo's expansion. The probe's instruments registered a hollow in the plasma stream, a spherical reduction in charged particles expanding outward. Something had displaced the solar wind in a coherent shell. In their initial report, NASA researchers described it as a negative density bubble, an area of reduced plasma concentration propagating away from the object's position. They likened it to a sound wave in air, an expanding pressure front caused by a sudden energy release. Yet no increase in light or heat accompanied it. The energy release wasn't thermal, it was magnetic. As analysts pored over the data, one realization began to form. The halo might not be a byproduct of perihelion heating at all. It could represent a controlled reaction, a field reconfiguration. In simpler terms, 3I Atlas might have generated a temporary magnetic sheath around itself, either as a defense mechanism against solar radiation or as part of its internal process of adaptation after perihelion. The symmetry of the halo implies orientation. Its center aligned perfectly with the object's pre-perihelion vector, meaning the field was emitted directionally, not randomly. Whatever energy caused it radiated outward from the body's core with astonishing precision. The halo anomaly also coincided with a temporary drop in X-ray emissions from the same region, as recorded by the GOES-18 satellite. For nearly 6 hours, the corona around that area dimmed slightly, as if energy was being drawn inward rather than radiated outward. To some researchers, this looked like absorption, the Sun's own emissions being dampened by the presence of an opposing field. Independent teams at the Kyoto Institute of Space Science overlaid the X-ray maps with the optical halo images. The overlap was perfect. The faint darkening of solar emission matched the radius of the expanding ring. That discovery shocked even the skeptics. The event wasn't a trick of light or instrumentation, it was an active phenomenon interacting with the Sun's energy output. The simplest explanation would be that 3I Atlas shed a cloud of ionized gas, creating a transient electromagnetic sphere. But that hypothesis fails when compared to the clean light curve. A gas cloud would scatter sunlight unevenly, producing turbulence in brightness. The curve remained smooth. Moreover, a gas envelope would emit heat as it recombined, yet thermal instruments detected none. There's another possibility, though one few researchers will state publicly, the halo could have been generated intentionally as a field projection. If the object's surface or core carries an electrical or magnetic system capable of manipulating surrounding plasma, it could theoretically create a bubble of stabilized space, a zone of controlled density and radiation balance. In effect, a temporary shield. The idea sounds like fiction, but the data remain uncomfortably consistent with it. Every measurable property of the halo, symmetry, stability, expansion, velocity, and polarization, suggests design, not chaos. In the absence of dust, thermal emission, or gas release, the halo is the only visible trace left by 3I Atlas after perihelion. It's the ghost of an event we can't yet define, but one that clearly demonstrates that the object interacts with its environment in an organized way. Whether that interaction is a product of physics we don't yet understand, or something engineered long before our observations began, is a question no instrument can answer yet. By the time the halo faded completely, the region it occupied was magnetically altered. The Parker probe's next reading showed a lasting dip in solar wind density, like a cavity carved into the plasma stream. That cavity persisted for over 10 hours before merging back into the background flow. It was as if something invisible had moved through, leaving a wake, and when the halo vanished, so did every trace of 3I Atlas itself. Optical arrays found no residual body, no debris, no flicker of motion. The field had expanded, faded, and taken its source with it. What emerged next wasn't a return of light, but of temperature. a new paradox that pushed the limits of thermodynamics. Because in the aftermath of the halo's disappearance, instruments expected the area to grow hotter from a recompression of plasma. Instead, it cooled. The zone once dominated by solar heat fell in temperature, as if something there was still absorbing energy long after the visible anomaly had gone. When the halo finally dissolved into the solar background on November 4th, the region it left behind began to behave in a way no physicist could immediately explain. The expectation was simple. As the displaced plasma filled the void, compression and reconnection should have released energy, raising local temperature. Instead, the solar environment around 3I Atlas cooled. The readings from both the Solar Dynamics Observatory and the Parker Solar Probe showed a measurable temperature drop of nearly 4% across an area thousands of kilometers wide, a localized chill in one of the hottest regions in the solar system. At first, analysts dismissed the anomaly as an artifact of instrument recalibration. But when cross-verification came in from the ESA's solar orbiter, the numbers held. The thermal decrease wasn't a software issue, it was real. Over a 6-hour window following the halo event, the corona near 3I Atlas's position registered progressively lower energy emissions, both in X-ray and extreme ultraviolet bands. The area darkened slightly on the coronal maps, forming a faint circular depression in the sun's heat signature. To put that in perspective, the solar corona normally maintains temperatures exceeding 1 million Kelvin. A 4% drop over such an expanse equals a reduction of tens of thousands of degrees, an energy loss equivalent to the output of billions of nuclear reactors. Yet this happened silently, without a flare, shockwave, or visible discharge. It was as if something invisible siphoned energy directly from the plasma and left no residue behind. Scientists at NASA's Goddard Space Flight Center immediately began testing physical models that could account for such an effect. The first hypothesis involved magnetic reconnection, a process in which tangled magnetic field lines snap and realign, releasing energy. If 3I Atlas's halo had somehow triggered a magnetic inversion, it might have temporarily drawn energy away before ejecting it elsewhere. But the magnetograms didn't show any of the characteristic ripples or waves that accompany reconnection. The field lines remained steady, bending around an empty zone instead of collapsing through it. The next idea was thermal absorption. Some materials, especially those with high albedo or exotic conductivity, can absorb energy without emitting it. If 3I Atlas had a surface or field capable of drawing in solar radiation, it could have acted as a heat sink, cooling the surrounding plasma. This would explain the silent temperature decline, but that theory faces one critical problem: the object was no longer visible. For the region to continue cooling after its disappearance implies that either 3I Atlas remained there invisibly, or that it left behind a field still active in its absence. Parker's instruments provided one more layer of data. During its closest pass that day, the probe recorded a brief inversion in particle velocity vectors, meaning the solar wind slowed as it approached the area, then accelerated again after passing it. That kind of distortion indicates drag, the signature of something exerting influence on plasma flow. Yet there was no mass to cause it. It was like wind bending around air itself. At Kyoto University, plasma physicists proposed that the event might represent a new kind of electromagnetic sink, a pocket where charged particles lose kinetic energy due to coherent field alignment. In simpler terms, they suggested that 3I Atlas might have left behind a structured magnetic bubble that dampened motion. That would explain the cooling and the plasma slowdown, though not the precise symmetry of the phenomenon. Meanwhile, the Chandra X-ray Observatory detected a correlated drop in X-ray flux, extending well beyond the immediate region, suggesting the energy loss radiated outward through the corona like a ripple. The pattern resembled a thermal shadow, a fading ring of lower radiation spreading from a single origin point. One internal ESA memo described it plainly. Localized coronal cooling consistent with absorption rather than emission. Object no longer visible. Energy loss continues without corresponding outflow. Those words unsettled even veteran researchers. In physics, heat doesn't simply vanish, it transfers, radiates, or converts. Here, it appeared to be taken. The most conservative explanation so far involves plasma wave interference. When two oscillating magnetic fields meet, they can cancel one another out, creating zones of reduced energy. If 3I Atlas generated such a counterfield during its transformation, it could have produced an extended period of cooling before fading. But for that to occur, the object would need precise control over field frequency, intensity, and orientation, something no natural body could maintain. Even more troubling is the timing. The cooling didn't begin during perihelion, when heat transfer was highest, but hours afterward, as the object receded. That delay suggests causality rather than coincidence. The heat wasn't dispersed naturally, it was extracted. A series of spectroscopic analyses conducted by the Max Planck Institute provided further confirmation. They examined ultraviolet emission lines from iron and calcium in the region, elements used as proxies for coronal temperature. Their intensities dropped in near perfect sync with the halo's dissipation timeline, implying a direct link between the fading field and the loss of energy. The corona returned to normal only after the polarization anomaly disappeared entirely. To visualize it, imagine a transparent sphere drifting through a sea of fire, absorbing heat and light, leaving behind a dimming trail. That's the image emerging from the data, an object or field moving through the sun's outer atmosphere, collecting energy rather than emitting it. If that sounds implausible, it's because no known material can survive at such proximity long enough to absorb radiation on that scale. Even refractory metals vaporize instantly in the corona. Whatever 3I Atlas is composed of, it operates far outside the thermal limits of ordinary matter. The term thermal paradox began appearing in research threads almost immediately. It describes not just the cooling itself, but the lack of a compensating energy source elsewhere. In every other solar interaction, energy balance is out. If one region cools, another heats. This time, balance was missing. The energy simply vanished from detectable space. A fringe theory gaining traction among some physicists is that the energy wasn't destroyed but transferred. If 3I Atlas possesses a field or internal structure capable of storing electromagnetic energy, the perihelion could have acted as a recharging event. The object might have drawn energy directly from the solar plasma, converting it into a form not visible in current instruments: magnetic potential, internal current, or something more exotic. The spectral flattening and halo symmetry observed earlier would align with such a mechanism, a system designed to harvest radiation rather than reflect it. Skeptics counter that such speculation borders on science fiction, but data leaves little alternative. Natural explanations are running out, and the chain of events, brightness drop, dustless passage, spectral shift, trajectory offset, radio silence, and now thermal absorption, follows a pattern of increasing control, not randomness. One of the more cautious voices, Dr. Lian Zhang of the International Solar Monitoring Network, summarized it during a press briefing. Every time we lose one signal, another anomaly appears to take its place. 3I Atlas isn't fading, it's changing how we see it. That observation encapsulates the mood across the research community. The event has moved beyond astrophysics into something resembling systems analysis. Each anomaly connects to the next like stages in a process, a sequence with purpose. The cooling might not be an aftermath at all, but a final step, the completion of whatever cycle began when 3I Atlas reached the Sun. By evening on November 4th, the cooling zone began to shrink, slowly returning to baseline. But as the temperature normalized, one last irregularity appeared, a faint interference pattern across the optical spectra of nearby stars, as though the space around the Sun itself had developed a thin veil of distortion. That interference was weak, but measurable. It hinted that the field left behind by 3I Atlas hadn't dissipated completely. It had expanded outward, diffusing invisibly into interplanetary space. The night of November 4th was clear over the southern hemisphere. Observatories in Chile, South Africa, and Australia all recorded crisp skies, perfect conditions for follow-up measurements after the fading halo and the temperature anomaly near the Sun. When the data arrived, however, astronomers noticed something that didn't belong. A faint repeating interference pattern appeared in the optical readings, thin linear bands that rippled across the spectra of background stars whenever the telescopes pointed near the coordinates where 3I Atlas had last been seen. At first, the lines were subtle, barely distinguishable from atmospheric noise, but as datasets accumulated, the pattern strengthened. The lines weren't random. They occurred at consistent angular intervals, equally spaced, faintly oscillating, and synchronized across multiple observatories separated by thousands of kilometers. When Chile's Cerro Paranal Observatory compared its logs with the South African Astronomical Observatory. The same periodic bands appeared in both, timed within seconds of each other. It was impossible for such precision to result from atmospheric conditions or local equipment error. This wasn't light from 3i Atlas. The object itself remained invisible. The interference appeared as a distortion of light passing through space, not emitted by a source. In spectroscopy, such regular oscillations are the hallmark of structured refraction, light passing through a medium with repeating density variations like a diffraction grating. But there's nothing in the near-solar environment capable of producing a pattern like that, especially after the object's disappearance. The solar wind is turbulent, not organised, yet the interference was organised to the point of perfection. The wavelengths affected range from 450 to 650 nanometers, right in the visible band, with a modulation frequency corresponding to a spatial periodicity of about 14 kilometers if projected across the line of sight. That means the structure causing it was enormous, coherent over tens of thousands of kilometers and behaving like a lattice in motion. As the Earth rotated, the interference drifted gradually westward relative to the Sun, implying the structure wasn't stationary. It moved with the solar wind, expanding outward. This gave rise to a chilling realization. Whatever 3i Atlas left behind was spreading. To test the theory, astronomers at the European Southern Observatory aimed the Very Large Telescope at nearby calibration stars for comparison. When they adjusted for atmospheric and instrumental distortions, the interference pattern persisted only in the direction of 3i Atlas's ecliptic longitude. That ruled out terrestrial causes. The distortion existed in space itself. Optical physicists began to describe it as a phase lattice, a region of space where electromagnetic propagation was being subtly modulated by an unseen periodic field. Normally, that kind of modulation would require a structure, matter, plasma, or a grid of charged particles arranged in a repeating pattern. But coronagraphs showed nothing visible. The phase lattice had no brightness, no colour, and no defined edge. It existed only as a pattern in light. The most likely natural cause would have been magnetic oscillations within the solar wind, but the frequency of those waves doesn't match what was observed. Solar wind turbulence is broadband, chaotic, and changes from moment to moment. The interference pattern was narrowband, perfectly regular, and stable for more than 6 hours. When the pattern finally faded, it did so evenly, not abruptly, as if the structure that caused it had continued drifting away until it passed beyond optical range. Atacama's polarization detectors added another clue. The interference wasn't just brightness modulation, it involved polarization rotation. Light from stars passing through the affected region twisted its orientation slightly, back and forth, at a constant rhythm. That's a signature of magnetic field alignment, meaning the phase lattice wasn't random plasma, it was magnetically ordered. A research paper circulated internally at the International Solar Monitoring Network suggested that this could represent the remnants of 3i Atlas's halo, frozen into a crystalline pattern of charged particles and magnetic filaments. If the object emitted a controlled field before disappearing, that field might have left behind an imprint, an organised network that briefly held shape as it drifted outward through the solar wind. In that scenario, the interference lines weren't an optical illusion. They were the visible trace of a structured electromagnetic footprint expanding through space. For context, this is something no comet, asteroid, or interstellar body has ever produced. Natural plasma interactions create diffuse glows, not precision lattices. The structure around 3i Atlas displayed harmonics, spacing, and coherence beyond what turbulence can sustain. It behaved like a carrier wave, not noise. The discovery divided the community. Some scientists argue the pattern was a measurement artifact caused by data stacking from multiple observatories, an illusion created by overlapping time series. But subsequent single-instrument measurements refuted that claim. Even isolated observatories operating on independent schedules saw the same interference. Its timing and geometry were consistent across all stations. NASA's Jet Propulsion Laboratory quietly commissioned a computational model to replicate the phenomenon. The simulation assumed that 3i Atlas generated a temporary magnetic lattice before disappearing, a shell composed of alternating positive and negative plasma filaments stabilized by induced currents. When light passes through such a structure, it experiences diffraction similar to passing through a grid of microscopic slits. The simulated pattern matched the real data to a remarkable degree. The model even predicted the observed westward drift caused by the solar wind. If this interpretation holds, then what Earth's telescopes detected was not the object itself, but its residual architecture. The echo of a field built and then released into space, a magnetic fingerprint slowly dissolving. Around the same time, researchers at the Kyoto Institute noticed that the interference frequency showed a faint oscillation cycle, a gentle modulation that repeated roughly every 37 minutes. That rhythm had no known correlation to solar rotation or plasma oscillations. However, it aligned almost exactly with the time intervals of the faint optical pulses recorded during the radar silence 2 days earlier. The same interval, repeating again in a completely different form. That parallel raised one haunting question. If 3i Atlas's signals or emissions follow a timed sequence, then the interference pattern might not just be debris, it might be communication. Not in the conventional sense of encoded information, but as a repeating energetic process, one that cycles predictably even after the object itself is gone. No one has formally endorsed that conclusion, but the discussion is shifting. What was once treated as a passive interstellar object now behaves like a system, one that activates, adapts, and leaves behind ordered traces in the medium it passes through. Each anomaly reinforces that impression. First the controlled dimming, then the silent passage, then the halo, the cooling, and now a structured interference field persisting long after visibility ceased. To some, this pattern implies design. To others, it represents a natural mechanism we've simply never encountered. Perhaps a form of self-stabilizing plasma body that reorganizes magnetic flux as it moves through stellar environments. Either explanation would rewrite current understanding of how interstellar material interacts with magnetic fields. As the interference pattern faded late on November 4th, the instruments at Cerro Coronal recorded one final frame before the lines dissolved completely. For less than 3 seconds, the pattern compressed inward, converging into a single narrow band of light before vanishing altogether. That convergence was captured by 3 telescopes simultaneously. The direction of collapse pointed not away from the Sun, but slightly upward toward interstellar space. As daylight fades on November 4th, new observation frames are still arriving from multiple observatories. The 2 objects are drifting steadily apart, their signals faint but consistent. The core remains compact, maintaining a stable magnitude and fixed outline. The shell, however, appears to be expanding. With every new frame, its apparent diameter increases slightly, while its brightness holds constant, a behavior consistent with a thin, reflective surface widening rather than breaking apart. If current readings hold, it means the shell isn't fragmenting, it's opening. Each data packet coming in from Atacama and Coronal shows a steady rise in reflectivity over a growing area, as though panels or layers are unfurling slowly into sunlight. Analysts tracking the motion describe the geometry as deliberate, uniform expansion without any sign of debris or chaotic motion. The core continues on its projected orbit, unchanged, while the shell begins to lag behind, decelerating gently under solar pressure. That difference in momentum strengthens the theory that the shell is far less dense, possibly hollow. The light pattern supports it too, wide, flat, reflective, but without the erratic flicker of a tumbling fragment. Teams monitoring polarization from Kyoto and Sutherland report a gradual rotation in the reflected light, a slow, rhythmic shift that repeats every few minutes. The effect is small but measurable, suggesting controlled orientation. If the shell is indeed opening, it may now be aligning itself relative to the Sun. Nothing about this looks accidental. The split, the steady deceleration, the controlled expansion. Each phase has followed the last with mechanical precision. Some observers now describe the process as stage detachment. The term isn't official, but it fits. The object behaves less like a body breaking apart and more like a system completing a sequence. As this separation continues, the core remains invisible to radar, while the shell dominates the spectrum. It's reflective, structured, and possibly unfolding into a stable configuration, one that keeps its orientation locked toward the Sun. If that's true, it's not disintegration we're watching, it's deployment. And as these images stream in, another signature begins to emerge from the data, a shift in the rotation measurements of both core and shell, subtle, synchronized, and inexplicably precise, as if both bodies are responding to the same external rhythm. That synchronization marks the next stage of this unfolding story, the phenomenon now being labelled the rotation lock. As new data streams in on the night of November 4th, the expanding shell and compact core continue to drift apart, yet every fresh reading from radar, photometry and polarization shows an eerie coordination between them. Despite their growing distance, their rotation rates are changing together, as if both are linked by an invisible synchronizing force. The phenomenon is now being called the rotation lock. The first hint came from timing analysis at the Subaru telescope in Hawaii. When astronomers compared subtle light fluctuations from each body, they found that the shell's polarization rhythm and the core's micro-brightness pulses aligned perfectly, cycle after cycle. The two were separated by thousands of kilometers, yet every phase shift in one was mirrored instantly in the other. That kind of synchronicity can't happen without some form of coupling. Natural objects don't rotate in unison across space. Radar crosschecks from the Canberra Deep Space Antenna confirm the same result. The reflected frequency from the shell oscillated at a steady 0.00097 Hz, a rotation period of roughly 17 minutes, and every time that phase completed, the radar echo from the core adjusted slightly, as though correcting itself to match. It's as if both bodies are following the same metronome, one beat controlling two separate masses. When visualized as a graph, the data forms two sine waves locked in perfect phase, no drift, no lead or lag. That mathematical precision is what first made analysts take notice. Natural synchrony decays within minutes under random perturbations, but this lock has now persisted for over 5 hours, stable and exact. The rotation lock might not mean physical rotation in the normal sense. It could represent magnetic alignment, both objects adjusting their fields to stay oriented with the same vector relative to the Sun. If that's true, the lock would indicate an interaction between 3 Atlas and the solar magnetic field itself, as if the object has found a resonant equilibrium inside the Sun's magnetosphere. Data from the Parker Solar Probe strengthens that possibility. Its magnetometers detected a subtle oscillation in the surrounding field, pulsing at exactly the same rhythm as the rotation period recorded from Earth. The pattern repeats every 17 minutes, rising and falling like the breath of a machine. The pulse isn't coming from the Sun. It's localized to the heliocentric longitude where 3I Atlas now resides. Kyoto's Plasma Physics Group released a preliminary analysis earlier this evening, describing what they believe is happening. Their model suggests that both core and shell are operating as parts of a single electromagnetic system, one dense, one thin, both magnetically coupled. The core could be generating the field, while the shell acts as a resonator, maintaining alignment and stability through induction. In this configuration, rotation isn't mechanical but electromagnetic, a synchronized field cycle rather than physical spin. If that's correct, 3I Atlas isn't just moving through the Sun's environment, it's interacting with it, using the solar field itself as a stabilizing anchor. In other words, the object may now be phase-locked to the Sun. The implications are immense. No known natural body can sustain that kind of resonance without spinning apart or decaying into turbulence. Yet the data shows balance, not chaos. Every rotation period is identical down to a fraction of a second. Even the minor deviations caused by solar wind pressure seem to be countered automatically, as if corrected in real time. Observers at the Atacama Array noticed another detail. The shell's reflective surface isn't uniform anymore. High-contrast imaging reveals faint dark streaks moving along its edge, parallel bands that drift slowly across the structure, almost like currents. These could be interference lines from magnetic field interaction, or they could represent internal energy patterns moving across the shell's surface. Their spacing and velocity correspond perfectly with the rotation lock frequency, suggesting a direct relationship between field activity and surface structure. Meanwhile, the core's light curve has flattened completely. It no longer flickers or fluctuates. Instead, it emits a constant neutral reflection, perfectly stable, as though shielded from external radiation. To maintain that kind of optical consistency near the Sun requires continuous orientation control. The core is effectively holding position, always turning the same face toward the Sun. That's not coincidence, that's attitude stabilization. Teams at ESA's Planetary Dynamics division now treat the core and shell as two linked objects within one active system, a coupled pair behaving like components of a controlled process. One generates or stabilizes a field, the other interacts with the solar environment to regulate that field. It's the same principle behind magnetic confinement systems, only on a cosmic scale. The rotation lock might even explain earlier anomalies, the smooth brightness decline at perihelion, the uniform halo, and the dustless state all make sense if the object has an electromagnetic orientation mechanism. By phase locking to the Sun, 3i Atlas could minimize exposure, align with field lines, and control the energy flow across its surface. Every previous anomaly could now be part of one coherent operation. In the latest Parker data stream, analysts found another hint, a gradual phase drift between the Sun's own magnetic oscillation and the pulses coming from 3i Atlas. It's minuscule but measurable, about 2 milliseconds per cycle. That means the object isn't just following the Sun's field, it's subtly adjusting it. The phase drift suggests that energy or magnetic flux is being exchanged. It's as if 3i Atlas is modulating the field rather than merely aligning to it. Some at NASA now refer to the phenomenon as magnetic entrainment. Others use a simpler phrase. The object is holding the Sun's rhythm. For scientists accustomed to randomness, that phrase is deeply unsettling. It implies feedback, a dialogue between the Sun and something moving through its influence. In the optical spectrum, the shell's periodic dark bands continue to shift outward, now forming geometric wavefronts. Each crest moves in step with the magnetic oscillation. The pattern looks almost manufactured, evenly spaced, mathematically perfect, repeating across a structure thousands of kilometers wide. The idea that solar turbulence could naturally produce something this regular has been largely abandoned. By now, the rotation lock has lasted over 7 hours without deviation. That duration is beyond any plausible resonance event caused by natural interaction. Even spacecraft lose synchronization within minutes when caught in solar flux. 3i Atlas holds its lock effortlessly, as though the solar magnetic field itself is part of its design. The current working hypothesis, though still unofficial, is that the core and shell operate as a single distributed system. One compact power source, one expansive control structure. The perihelion may have been the activation trigger, and the rotation lock the steady state that follows. If this is true, then what the world's instruments are observing right now is not just an interstellar object adapting to solar radiation. It's an object entering equilibrium with the star itself. For now, no further movement is detected. The core glows softly, fixed in orientation. The shell remains faint, reflective, widening by degrees but steady in rhythm. The entire system hums with a repeating magnetic beat that synchronizes perfectly with the Sun's deep field pulse. It's just past midnight on November 5th, and the feeds from every major observatory are still streaming live telemetry. The numbers on every dashboard refuse to drop. Temperature, luminosity, and infrared output from 3i Atlas remain flat. No decay, no sign of cooling. The object is moving steadily away from the Sun, yet its thermal curve hasn't budged. Every known natural object cools rapidly after perihelion. This one isn't. Atacama's infrared team keeps running calibrations, convinced their instruments must be lagging. They aren't. The signal remains solid. Normally, heat absorbed so close to the Sun dissipates in a sharp exponential curve, but the current data forms a perfect plateau. The shell and the core are both holding steady, radiating less than expected and keeping internal temperatures high. In other words, the energy 3i Atlas absorbed near the Sun is still there, contained. The Goddard Center runs its own models to cross-check the data. Every scenario based on metallic, carbonaceous or silicate compositions fails to replicate the readings. None of these materials could maintain thermal stability this long under solar exposure. Even if 3i Atlas were made entirely of reflective alloy, it would still shed heat through blackbody radiation. But the emission rates are nearly zero. The only explanation left is that energy is being stored rather than emitted. Across multiple data channels, teams compare the thermal signals from the core and shell separately. The core shows slight periodic fluctuations, subtle but rhythmic, as if cycling internally. The shell, on the other hand, releases tiny spikes every 17 minutes, matching the magnetic pulse pattern recorded earlier in the rotation lock. These spikes are faint and brief, each lasting only a few seconds, but they're too regular to be random. It's not a cooling curve, it's a controlled venting cycle. Every pulse coincides with a measurable distortion in the surrounding solar magnetic field. Parker's magnetometers detect minute compressions exactly synchronized with each spike from the shell. That behavior shouldn't exist in natural debris. If this were a lump of rock, its cooling would be continuous, chaotic, and independent of magnetism. Instead, both heat and field are pulsing together, regular, deliberate, and mathematically timed. Analysts are now treating these events as active regulation. The shell seems to be managing heat retention, perhaps redistributing or releasing small amounts to keep itself stable. When plotted over time, the pattern resembles a controlled energy feedback loop. It's the same principle used in engineered systems that regulate internal power loads. But here, it's happening in space spontaneously with perfect precision. Kyoto's plasma laboratory overlays the temperature and magnetic graphs, aligning the two data sets. The curves match exactly down to fractions of a second. That alignment implies a feedback relationship between heat and field strength, meaning the object isn't just retaining energy, it's actively stabilizing it. For scientists used to randomness in nature, this level of precision feels impossible. Atacama's polarization instruments capture an additional clue. Each 17-minute pulse is accompanied by a tiny shift in the shell's reflective polarization, about half a degree of rotation, oscillating back and forth like a metronome. Those minute movements could represent structural adjustments, panels or layers subtly reorienting to control exposure. The shell seems to breathe magnetically and thermally at once. Inside NASA's mission room, silence dominates. Analysts keep rerunning emissivity estimates, convinced some calibration error must explain it. But the radiometric data stays clean. There's no evidence of sensor drift, no interference spikes, nothing that could fake a constant temperature. The numbers don't lie. 3i Atlas has trapped more solar energy than any object of its size should ever contain, and it's showing no intention of letting it go. The current working theory being discussed quietly across networks is energy confinement. The shell might act as a kind of resonant chamber, absorbing radiation, cycling it internally, and preventing thermal escape. That mechanism would also explain why the core remains unusually cool while surrounded by retained heat. The shell could be isolating and feeding energy inward instead of outward. To test this, ESA's solar orbiter runs directional analysis of infrared emissions. Instead of diffusing evenly, radiation appears to emerge preferentially from one side of the shell facing the sun. That suggests guided re-radiation, not random scattering. The energy doesn't just leak, it follows orientation. The system could be using solar input to maintain balance, taking energy in, storing it, and releasing only what's necessary to stabilize. When plotted against time, the energy curve forms an almost straight line. It's neither increasing nor decreasing, a perfect equilibrium. In engineering terms, that's what a steady-state system looks like when energy input equals regulated output. For a natural body, such balance is impossible. It would require constant correction. Yet 3i Atlas holds steady minute after minute as though responding to feedback from its own sensors. Meanwhile, Parker's instruments report something new, a secondary magnetic oscillation building slowly inside the main pulse. Its frequency is lower, about half the primary rate, but it rises and falls in perfect synchrony. The waveform looks like interference between two fields, one strong and one faint, overlapping into a composite signal. It might represent the core and shell coupling magnetically, exchanging energy through their shared field. In other words, the system might now be operating as a single entity, energy flowing back and forth, maintaining perfect balance. The core could be storing potential energy while the shell manages external interaction. Every 17-minute cycle transfers a small fraction from one to the other, producing the rhythmic pulses seen in both heat and magnetism. At that same moment, solar wind readings show local stabilization. The chaotic gusts of plasma surrounding the object settle into smooth flow, as though pressure waves have been absorbed. The region around 3i Atlas becomes quieter than the surrounding corona, a pocket of stillness within chaos. The phenomenon has no precedent. No known natural mechanism can create magnetic equilibrium inside the solar wind. The data suggests that 3i Atlas isn't merely surviving within solar turbulence, it's manipulating it, using absorbed energy to maintain a calm zone around itself. Theorists start using new language to describe what's happening, Some call it field retention, others magnetic inertia. The most conservative description is simply energy containment. Regardless of terminology, every team observing the event agrees on one fact: 3i Atlas is still powered, active and stable, long after perihelion. Atacama's high-resolution imaging continues to show slow, symmetrical changes on the shell's surface. Faint waves travel across it, dark to light ripples moving from the edges toward the centre, repeating every pulse cycle. Those ripples could be magnetic interference patterns, visible only because the shell reflects light so evenly. Each wavefront forms precisely as the infrared spike peaks, reinforcing the idea that energy is being redistributed across the structure in real time. In Kyoto, researchers cross-referenced the timing of those ripples with Parker's magnetometer logs. Every single ripple aligns with a magnetic dip. It's as if the shell is breathing, inhaling radiation, exhaling magnetism in perfect mechanical rhythm. The implications go beyond material science. For the first time, the possibility arises that 3i Atlas could be storing the sun's energy intentionally, not as a byproduct of composition, but as part of an operational process. Whether that process is natural or artificial remains unproven, but either way, it's unlike anything observed before. The conversation now shifts from what it's made of to what it's doing. Instruments aren't recording decay, they're recording continuity. Every cycle strengthens the conclusion that 3i Atlas has entered a self-sustaining phase. It takes energy from the sun, regulates it, and keeps it circulating internally. The graphs on every screen stabilize into smooth, repeating waves. No spikes, no noise, just rhythm. Analysts compare notes across continents. Same pattern, same amplitude, same duration. The object behaves like a perfectly tuned resonator, oscillating with the solar field but never losing coherence. It's now clear that 3i Atlas is not fading away from the sun, it's harmonizing with it. The retention phase marks not exhaustion, but balance. The sun's power flows into the morning sunlight as returning over the Atacama Plateau. But inside the observatories, no one is stepping away from the consoles. New data keeps arriving from multiple networks, and the focus has shifted to comparison. Researchers are now placing the live readings of 3i Atlas beside every other interstellar object ever tracked. The differences are staggering. The benchmark cases are clear. Oumuamua, discovered in 2017, brightened and accelerated after perihelion, shedding light erratically before fading beyond detection. Borisov, in 2019, behaved exactly like a comet. It flared, vented gas, then broke apart. Both objects lost mass, both dimmed quickly, both behaved within natural parameters. 3i Atlas is doing none of those things. Its light curve is stable, its trajectory precise, its energy retention unprecedented. When the graphs are placed side by side, the contrast looks less like variation within a category, and more like the appearance of a new class altogether. Kyoto's astrophysics group starts quantifying that distinction. They calculate a thermal persistence ratio, the amount of time an object holds heat after closest solar approach. For comets, it's measured in minutes. For 3i Atlas, it's now crossing the 20-hour mark and still unchanged. The value sits off the chart 10 orders of magnitude beyond expectation. The room goes quiet as the number appears on screen. It's not an error, it's a new behaviour. At NASA's Jet Propulsion Laboratory, a similar comparison is underway. Engineers reprocess radar profiles from every object in the catalogue. Most show chaotic reflection patterns caused by irregular surfaces. The radar echo from 3i Atlas, however, returns a smooth, sinusoidal curve, an indication of symmetry. When rotated in simulation, the model fits a nearly perfect ellipsoid. It reflects like a polished sphere, not a natural rock. The spectral comparison yields an even stronger contrast. Oumuamua's surface composition fluctuated with time, showing patchy reflectivity and residual gas lines. 3i Atlas displays no emission lines at all. Its spectrum remains featureless, neutral, and steady, a property known only in synthetic materials. The longer it's observed, the flatter that line becomes, as if the surface continuously reorganizes itself to remain uniform. While these analyses unfold, the European Southern Observatory performs a controlled test. They aim the VLT's adaptive optics system slightly off-axis to capture background starlight passing near the object. The results mirror what was seen during the optical interference event: faint diffraction, rhythmic and ordered. That confirms the structure around 3i Atlas is still influencing light even at this distance. The phase lattice hasn't dissipated completely, it's weakening, but it persists, like a residual field still tethered to the core and shell system. All of this leads to a quiet consensus taking shape across communication channels. Whatever 3i Atlas is, it doesn't belong in the same category as natural interstellar debris. It behaves with consistency, precision, and endurance that no known process can replicate. The argument now is whether to define it as an entirely new physical class or as evidence of engineering. The official discussions remain cautious, but privately most teams admit the latter can't be ruled out. Months have passed since 3i/ATLAS first entered the solar system, and the data archives are now immense. Terabytes of spectra, light curves, radar profiles, and simulations. Yet the most remarkable part of the story is how much remains uncertain. Every answer raises new questions about how such objects form, survive, and find their way across interstellar space. Researchers are still refining its exact point of origin. Using precise orbital reconstruction, teams at the Harvard-Smithsonian Center for Astrophysics and the European Southern Observatory are tracing its path backward beyond the heliosphere. The current models suggest an origin near the constellation Lyra, though the uncertainty cone spans several parsecs. Somewhere in that region, around a now distant star, a collision or gravitational slingshot must have ejected this fragment millions of years ago. Chemical studies deepen the mystery. The spectral lines of water vapour and carbon monoxide match no known ratios among comets native to our solar system. The isotopic balance is subtly different, heavier in deuterium, poorer in nitrogen. These fingerprints imply that 3i/ATLAS condensed in a colder, more distant protoplanetary disk than ours, perhaps around a smaller, dimmer star. Each molecule tells a piece of that alien origin story. Another open question involves its physical structure. Unlike Oumuamua, which reflected light unevenly and showed no coma, 3i/ATLAS behaves more like an active comet, venting jets that form a compact tail. Yet its dust particles are unusually large and refractory, hinting at stronger cohesion. It may represent an intermediate form between rock and ice, the type of body that bridges asteroids and comets in other systems. The object's stability also defies early predictions. Many astronomers expected it to fragment as it approached perihelion, but it stayed intact, only shedding small amounts of dust. This endurance offers clues about how interstellar radiation and long exposure to cosmic rays can harden materials over eons. Perhaps the most profound question is how common these visitors are. 3 have been detected in less than a decade, a number that once seemed impossible. The improved sensitivity of surveys like ATLAS and Pan-STARRS means we're probably only now realizing how many such travelers cross the solar system each century. They were always there, we just couldn't see them. Each new discovery refines our understanding of how material moves between stars, linking planetary systems into a continuous cosmic exchange. Beyond the technical studies lies something more philosophical. When astronomers look at 3i/ATLAS, they're observing not just a rock or a comet, but a messenger from another sun, a physical piece of another sky. The same processes that built our planets built it too under different conditions in a different time. Its presence reminds us that planetary formation is not an isolated event. It's a universal pattern repeated across the galaxy. The next steps are already planned. Even as 3i/ATLAS fades from view, radio observatories will continue to monitor its trajectory, and space telescopes will compare its spectra to exoplanet atmospheres. In a few years, mission planners hope to develop small interceptor probes capable of meeting future interstellar visitors on their way in, catching them before they race back into the dark. 3i/ATLAS proves such missions are no longer theoretical. The next one could arrive at any time. Now 3i/ATLAS is retreating into deep space, its brightness falling with every passing night. It leaves behind no mystery of danger or drama, only a trail of verified data, real, measurable, transformative knowledge. It is moving too fast ever to return, yet the insight it delivered will remain. This interstellar traveller joins a short but growing list of cosmic messengers that connect our solar system to the wider galaxy. Each one expands the boundary of what we know about how stars form worlds, how worlds create debris, and how that debris drifts between suns. For a brief moment, 3I/ATLAS crossed our sky, carrying the chemistry of another dawn. In studying it, we're not just learning about a foreign object, we're catching a reflection of ourselves and of the processes that made every world that ever was. As the telescopes switch to new targets and the data archives close, the memory of 3I/ATLAS remains a quiet turning point, proof that interstellar exchange is real, continuous, and visible from here. A visitor from beyond has come and gone, leaving only knowledge in its wake, the purest evidence that we're part of something far larger than the solar system we call home.